Welcome to the Deep Dive. You're here because you want to get a handle on complex ideas without your brain feeling like it's doing Olympic-level gymnastics.
Okay.
We take stacks of information and pull out the golden nuggets for you.
And today, we're excavating some fascinating insights from a 1993 paper by Andreas Dimitriou in quest of the functional architecture of the developing mind, the Aristotelian project.
Think of it as a kind of blueprint for how our minds build themselves.
Exactly. This paper is a deep dive itself, but our mission today is to really surface the core of Dimitriou's thinking on how our cognitive abilities take shape and how they're organized. By the end of this, you'll have a solid framework for understanding not just what we learn, but, well, how our ability to learn and think even comes to be.
hmm
So let's get into it. Dimitriou talks about a three-front model of mind development. What's the big picture here? Well, imagine your mind developing on three parallel tracks that are, constantly interacting. The first is the general processing system. This is like the raw power and efficiency of your mental engine. It drives your ability to learn new strategies and skills, kind of setting the upper limits on what you can potentially achieve cognitively.
So this is the engine room of our thinking, the like fundamental processing muscle.
Precisely, yeah. Then we have the hypercognitive system. Now, this is where our self-awareness and mental management come into play. It's a part of you that can step back and think about your own thinking, allowing you to regulate and direct your cognitive resources effectively.
The control tower, maybe?
Yeah.
Guiding all the mental traffic.
Yeah,
Making sure we're using our processing power wisely.
that's a great way to put it, yeah. And the third front involves what Dimitriou calls specialized structural systems, or SSS. These are like dedicated modules in your brain, each designed to handle specific types of information, different aspects of reality, like numbers or space or cause and effect. Think of them as specialized tools in your cognitive toolkit.
Okay, so instead of one Swiss Army knife for everything, we have different tools optimized for different jobs. Now, these three fronts don't just evolve haphazardly, right? There must be principles guiding their development.
Exactly. Dimitriou outlines 5 key organizational principles that explain how these systems emerge and operate.
5 principles. Okay, let's tackle the first one, the principle of domain specificity. What's the core idea there?
Well, this principle starts with a pretty intuitive idea. Reality isn't just one big blob, It's made up of different domains, like the world of objects, the world of numbers, the world of social interactions. And each of these has its own unique properties and rules. So, a cat behaves in fundamentally different ways than a mathematical equation does.
Right, yeah. Gravity affects the cat, but addition affects the numbers. Different rule books.
Exactly. And the second part of this principle is that our minds adapt to this varied reality by developing these specialized structural systems, the SSS. These SSSs are tailored to effectively interact with and understand these distinct domains. So basically, our minds develop different ways of thinking because the world itself is structured differently.
Okay, so our brains kind of mirror the complexity of the world by creating these specialized systems. What's the second principle then?
The principle of formal procedural specificity. This builds directly on the first one. It basically says that the mental operations we use within a particular SSS need to be, well, appropriate for the kind of reality it's dealing with. If you try to apply the wrong kind of mental operation, you'll likely just end up with confusion.
Like trying to understand a painting by analyzing its chemical composition. I mean, useful for some things perhaps, but it kind of misses the point of the artwork itself.
Precisely. It's about using the mental tools that are designed for the specific material you're working with to get, meaningful results.
Got it. Right tool for the right cognitive job. Makes sense. What's the third principle?
That's the principle of symbolic bias. This suggests that each SSS has a natural leaning towards the type of symbols that best represent its particular domain. And more than that, it's biased towards the symbols that allow for the most efficient processing within that domain.
So certain types of information just click better with certain ways of representing them. Is that it?
Absolutely, yeah. Think about trying to describe the layout of your house using only numbers. It would be incredibly cumbersome, right? But a mental image, or maybe a rough sketch, something leveraging our spatial imaginal SSS and its bias towards imagery, conveys that information much more directly.
Hmm.
Conversely, try calculating a restaurant bill using only mental images.
Yeah.
Numbers are clearly the more efficient symbolic system for that quantitative task.
Makes perfect sense. Some things are just naturally easier to think about in certain forms. Okay, what about the fourth principle?
The principle of subjective equivalence, distinctness of abilities. Now, this one is about how we experience our own thinking, because we have these different specialized systems, each with its own way of processing information and its own symbolic preferences, our experience of using them actually feels different.
So it's not just that the systems are different objectively, but it actually feels different to use them.
Exactly. When you're grappling with a spatial puzzle, it feels different than when you're trying to solve, say, a logic problem. This difference in our subjective experience, which arises from those first three principles we talked about, helps us to intuitively sense which mental tools are most appropriate for a given task. Similar cognitive experiences feel functionally equivalent, guiding us towards effective strategies. It's almost like your brain has an internal "this feels right" meter for different types of problems.
Ah, that's fascinating. Our own mental experience guides us.
Okay.
And the fifth principle.
The principle of developmental variation. This simply acknowledges that as we develop, we'll see both common patterns in how our cognitive abilities emerge, but also significant differences between individuals and even within the same individual across different abilities. This is due to the unique mix of experiences we have with different reality domains and the inherent way our minds are organized.
Right. So our personal journey through life shapes our cognitive landscape, even though there are some universal milestones in development. Okay, now let's dive into those specialized structural systems themselves. First up was the qualitative analytic SSS. What's its focus?
Right. So this system is all about the inherent qualities and characteristics of things. Its primary function is to analyze, to break down objects, ideas, or situations into their component parts and properties, like color, texture, function, or even abstract attributes.
So it's kind of the mental equivalent of taking something apart to see what it's made of.
Precisely, yeah. Once it's dissected these properties, the qualitative analytic SSS then builds conceptual frameworks by understanding the relationships between them, how these properties fit together to form categories or sequences. This is crucial for things like classifying objects
Or like understanding steps in a process, like
Yeah.
a recipe.
Exactly. Or understanding a series of events. Spot on.
Okay, what's the next SSS then?
That would be the spatial imaginal SSS. This one, as the name suggests, deals with the visual and spatial aspects of reality. It's about forming mental images, manipulating them, like mentally rotating an object, integrating different visual elements into a whole, and remembering spatial layouts.
Our inner GPS and visual artists is all rolled into one, maybe?
Exactly. That's a good way to put it. It's essential for navigating our physical environment, understanding maps, and even visualizing abstract concepts sometimes.
Okay, and then there's the quantitative relational SSS. That sounds like the math whiz of the group.
That's right. This system is concerned with quantifiable aspects of reality, anything that can be measured or counted. It's also inherently relational because, a quantity only really has meaning in comparison to others. Dimitrou breaks it down into key abilities. First, the ability to specify and represent quantities, like basic counting and using numbers.
The fundamental building blocks of math literacy, basically.
Yes. Exactly. Second, the abilities of dimensional directional construction. This involves understanding how quantities change and relate to each other, concepts like increase, decrease, and the nature of those changes, like linear, curved, etc. This is where we start to grasp the idea of variables.
Right, understanding trends and patterns in numerical data.
Exactly. And third, the abilities of dimensional directional coordination. This allows us to understand and work with relationships between different quantitative dimensions, which is vital for more advanced mathematical thinking, like ratios and proportions.
So moving from basic arithmetic to more complex mathematical relationships.
Mm-hmm.
Okay, what's the next specialized system?
That's the causal experimental SSS. This system is applied to understanding cause and effect relationships. It's about figuring out why things happen by identifying the key factors at play and building mental models of these causal connections.
Our inner detective, perhaps. Trying to solve the mysteries of why things work the way they do.
Precisely. A core ability here is combinatorial thinking, the capacity to systematically consider all possible combinations of factors that might be causing an effect. It also involves forming hypotheses, designing experiments to test those hypotheses, and constructing models to explain the results.
So it's not just passively observing, but actively testing and building explanations for cause and effect. Makes sense. And the final SSS.
The verbal propositional SSS. This system focuses on the formal relationships between mental operations rather than the specific content those operations are applied to. Its hallmark is the ability to separate the logical structure of an argument or a series of statements from its particular context and operate purely on that structure.
So it's about the underlying logic of an argument, regardless of whether we're talking about apples or oranges.
Exactly. While other SSSs might involve reasoning, this system is specifically geared towards the abstract rules of logic, allowing for deductive and inductive reasoning that isn't tied to a particular subject matter.
Okay, so we have these specialized systems for dealing with qualities, space, quantities, causes, and logical arguments. And each has its own way of working in preferred symbols, which leads to us experiencing them differently.
Precisely. And that's why, as the principle of subjective equivalence distinctness tells us, using these different systems feels distinct. The mental effort involved in quantitative reasoning might feel different from the mental imagery involved in spatial problem solving, right? And this subjective difference helps us recognize them as separate and choose the right one for the task at hand.
This all sounds very logical, very coherent. But was there actual research backing up these SSSs and principles?
Yes. The 1993 paper itself presented a study specifically designed to test the principle of domain specificity and the principle of symbolic bias. They looked at quantitative reality versus causal reality and numerical versus imaginal symbols.
Okay, how did they set up that experiment?
They created 4 sets of tasks: quantitative relational tasks using numbers, which they called QRN, quantitative relational tasks using imagery, PIGRI, causal experimental tasks using numbers, CEN, and causal experimental tasks using imagery, CEI.
Can you give us an example? Like, what might someone have to do in these tasks?
Sure. For a QRN task, you might see information about how much fertilizer different plants receive and how much they grow, maybe in a table, and you'd have to use the numbers to figure out which plant benefited most. A CEN task might give you a hypothesis, like more sunlight makes plants grow taller, and ask you to design a numerical experiment to test it, like saying how many plants you'd need, how much sun each gets, etc.
Okay, I see the number focus there. What about the imagery tasks then?
In the QRI tasks, participants learned how different visual cues, like maybe arrows or colored blocks, would change the amount of water in different containers shown in a picture. They'd then have to mentally apply these cues and figure out which container would end up with more water.
Hmm.
The CEI tasks were similar, using those same visual operators, but instead of focusing on the amount of water, they had to figure out the type of causal effect the visual cues were having on the water level, for example. One cue might always add water, another might always remove it, regardless of the starting amount.
Interesting distinction. And who are the participants in this study?
They tested a pretty diverse group of 163 individuals across 4 key developmental stages: 12, 14, 16, and 20 years old. This allowed them to see how these cognitive abilities might be structured at different points in adolescence and early adulthood.
And what did the results actually show? Did it support the model?
Yeah, using a statistical method called factor analysis, they found evidence supporting the idea that there are distinct underlying abilities for quantitative reasoning and causal reasoning that supports domain specificity and separate influences of whether the task was presented using numbers or images, supporting symbolic bias.
Okay.
They also found evidence for a more general cognitive ability that contributed to performance across all tasks. The way the data patterns aligned with their proposed model provided pretty strong support for the idea that our cognitive performance is influenced by both the domain of knowledge and the way that knowledge is represented.
So it wasn't just one general intelligence factor at play, but different specialized abilities were clearly distinct as well.
Right. Now, you mentioned the hypercognitive system earlier, the control tower. Let's dig deeper into its role. What exactly does it do? Okay. The hypercognitive system is essentially the brain's internal management system for all things cognitive. Demetrius sees it as the crucial interface between our thinking and the world around us, between the different specialized systems, the SSSS, and also between our basic processing power and those specialized systems.
You used hypercognition instead of the more common metacognition. Why the subtle difference in terminology? Is it important?
That's a good point. It is slightly different. While hypercognition includes what we typically think of as metacognition, like reflecting on our thinking after the fact, Dimitri uses the term hypercognition because this system is active not just after we've thought about something, but also before and during the process. It influences how we even approach a cognitive task in the first place. So it's a more encompassing idea of self-awareness and cognitive control that's active throughout.
Okay, so it's a proactive and ongoing management system, not just a post-thought reflection. Got it. How does it exert this control then?
Well, it works on 2 main levels. There's the macro developmental level, which shapes our overall understanding of how our minds work and how we learn. This includes what Demetria calls our theory of mind, which actually has 3 parts: our model of intelligence itself, what we think it means to be smart, our model of cognitive organization and functioning, how we understand different mental processes like memory and attention and how to use them effectively, and our model of ourselves as thinkers, our beliefs about our own cognitive strengths and weaknesses.
So our fundamental beliefs about our own minds and abilities. Okay, what about the micro-developmental level?
At this level, the micro level, the hypercognitive system is making more moment-to-moment decisions about our ongoing cognitive activity. Two key things happen here. It determines which specialized system, which SSS, is most relevant for the task at hand. He calls this the SSS task affiliation. And it makes decisions about how to use our mental strategies and processing resources most efficiently for that specific task.
So it's constantly assessing the situation and allocating the right mental tools and energy.
Right. Is there evidence for this hypercognitive system in action, like the SSS study?
Yes. A study by Demetrio and F. Clydes back in 1989 looked specifically at how well people are aware of different aspects of their own cognitive functioning. They wanted to see if individuals could accurately judge how similar or different tasks from various specialized systems were, how difficult they would find tasks of varying difficulty levels, and how successful they thought they were likely to be.
Okay, how did they go about measuring that self-awareness?
They tested a range of participants from around 12 to 22 years old using 8 different tasks that tapped into 4 of the specialized systems we discussed: causal experimental, quantitative relational, imaginal spatial, and verbal propositional. And for each system, they used one easier task, typically mastered around age 12, let's say, and one more difficult task, typically mastered around age 18. After attempting each task, participants then provided ratings about their experience.
What kind of ratings were they asked to give? Like specifically? They rated how similar pairs of tasks felt in terms of the mental operations involved. Some pairs were from the same SSS, some were from different ones. They also rated how difficult each task felt, based on the mental effort involved. And finally, they rated how confident they were that they had actually solved it correctly.
And what did their responses reveal? Did people have a good sense of this?
Yeah, the findings strongly suggested that our hypercognitive system provides a reasonably accurate internal map of our cognitive abilities. They found that patterns in the actual performance scores, the difficulty ratings people gave, and the success evaluations all align pretty well with the idea of distinct specialized systems.
Oh, really?
Yeah, for example, people rated tasks from the same SSS as more similar than tasks from different SSSs, which makes sense. And they consistently rated the objectively more advanced tasks as more difficult, aligning with their typical age of acquisition.
So our conscious awareness of our cognitive processes seems to reflect the underlying structure of our mental abilities. That's pretty compelling support for this idea of a hypercognitive control system. Okay, now let's move on to the processing system, the raw horsepower you mentioned earlier. What are its key features again?
Right. The processing system is the fundamental machinery for handling information. It's where we take in information, hold on to it, and manipulate it to achieve our mental goals. Demetrio proposes 3 core interconnected components: speed of processing, control of processing, and storage capacity.
Speed, control, and storage. Yeah, it sounds like the basic specs of a computer almost. Tell us more about how these work in our minds.
Okay. Speed of processing is simply how quickly we can execute basic mental operations efficiently, just raw speed. Control of processing is like our mental filter. It allows us to focus on goal-relevant information and ignore distractions or irrelevant stuff. And storage capacity refers to how much information we can actively hold in our mind and work with at any given time, often referred to as working memory.
And you mentioned they're interconnected. How do these 3 elements influence each other?
They absolutely work together. I mean, someone who can process information quickly can handle more pieces of information within a given time frame, right? This increased flow of information then requires more effective control mechanisms to filter out what's important. And with better speed and control, we can use our storage capacity more efficiently, holding on to relevant information just long enough to process it effectively without getting overloaded.
So they all kind of synergize to contribute to our overall mental efficiency. Is there research that looks at this processing system and how it relates to those specialized systems, the SSSs we talked about?
Yes, indeed. The same 1993 paper included a study that specifically examined the relationship between the processing system and the quantitative relational SSS, the math one.
Okay, what did that part of the study involve? How did they measure processing?
They used classic Stroop tasks, where you see the word blue written in red ink and have to say the ink color to measure processing speed and our ability to control interference. They also used storage tasks that involved remembering either a single digit presented briefly or the ratio between two digits.
Okay, Stroop and memory tasks. And how did they assess quantitative reasoning in this part of the study?
They used 4 different sets of math-related tasks. One focused on basic arithmetic problems, but with an increasing number of unknown operations you had to figure out. Another looked at proportional reasoning using mixtures of paint, like how much blue and yellow to make a specific green. A third involved solving algebraic equations of increasing complexity. And the fourth assessed the ability to understand quantitative relationships presented in tables, similar to the earlier task, but maybe more complex.
So a really comprehensive assessment of both basic processing abilities and more complex mathematical skills. What were the main findings here? Did processing matter?
Definitely. Through statistical analysis, specifically confirmatory factor analysis, they found evidence for a general underlying processing system factor and a separate general factor for quantitative relational ability. But importantly, they also found a statistical link suggesting that the efficiency of our general process system directly influences our performance on quantitative tasks.
That makes intuitive sense.
Ah,
I mean, a more powerful underlying engine would likely lead to better performance in specific cognitive domains like math, wouldn't it?
exactly.
Were there any interesting relationships found within the processing system itself? You said they were interconnected?
Yes. Their analysis suggested a kind of causal chain within the processing system. Processing speed seemed to influence our ability to control our attention, which in turn impacted our working memory capacity. They also found direct connections between that storage capacity and performance on basic arithmetic, which then linked further up to the more advanced quantitative abilities like proportional reasoning and algebra. This really supports the idea that these foundational processing abilities lay the groundwork for more complex cognitive skills within the specialized systems.
So it's a layered architecture, it seems, where the efficiency of our basic mental machinery has a cascading effect on our more specialized cognitive abilities. Fascinating. Now, out of all these systems, the processing system, hypercognition, and the SSSs typically develop as we age. Are there any broad patterns we can observe?
Yeah, Demetria outlines some general developmental trends. The processing system, for example, tends to show improvements in speed, control, and storage capacity throughout childhood and adolescence. There seems to be a period of more rapid change, often observed around the ages of 10 to 12.
Okay. What about hypercognition, our self-awareness and control system? How does that develop?
Well, the development of hypercognition involves a gradual increase in our understanding of our own mental processes. Young children, maybe around 2, 3 years old, start to develop a basic awareness of different mental functions, like knowing thinking is different from seeing. However, it's typically in early adolescence that individuals become more adept at identifying the underlying demands of cognitive tasks and consciously adjusting their strategies accordingly. And the development of a more sophisticated theory of mind, understanding our own and others' mental states in complex ways, often continues into early adulthood.
And what about the specialized structural systems? You gave us the quantitative relational SSS as an example earlier. Can you recap the typical developmental path for that one?
Sure, the development of the quantitative relational SSS begins with what are called proto-quantitative schemata in early childhood, around 3 to 5 years, where children develop an intuitive sense of quantity, just basic more and less. By 6, 7 years old, the ability to perform basic arithmetic operations is usually established. Then, the capacity to solve arithmetic problems with increasing complexity tends to develop between roughly 7 and 12 years old. Proportional reasoning skills often emerge a bit later, between maybe 11, 12, and 14, 15 years, and algebraic abilities tend to develop over a slightly broader range, maybe from about 8 up to 15 years, again with increasing complexity.
You mentioned symbolic encapsulation earlier as a key mechanism in the development of the quantitative relational SSS. Can you explain that a bit more? What does that mean?
Right. Symbolic encapsulation is a crucial process where we take more basic quantitative concepts or procedures, like those arithmetic operations, and represent them with more abstract symbols, like we see in algebra with X and Y. This allows us to manipulate these concepts at a higher, more abstract level without having to constantly think about the concrete quantities they might represent underneath. It's kind of like creating a powerful shorthand that allows us to handle more complex ideas efficiently.
I see. So it's about creating more powerful and versatile mental tools by abstracting away some of the specifics. Okay. Now let's talk about the driving forces behind all this development. What does this theory say about what actually causes these changes in our cognitive abilities?
Well, the theory proposes that developmental change is a synergistic process. What that means is that changes in one system, whether it's processing speed improving, or hypercognitive awareness getting sharper, or the sophistication of an SS increasing, can trigger changes in the other systems because they are all interconnected and influence each other.
Ah,
So, for example, improvements in processing speed might lead to an increased capacity in working memory. That increased capacity could then allow for more complex problem solving within a specialized system, say in math, which in turn might lead to a greater awareness of our own problem solving strategies at the hypercognitive level, making us better learners overall.
so it's like a chain reaction or maybe a positive feedback loop where progress in one area can fuel progress in others.
Mhm.
Are there different mechanisms at play for these different types of developmental changes? Or is it all the same process?
According to the theory, different kinds of developmental shifts might rely on different underlying mechanisms. For instance, the initial development of specific skills within an SSS, building upon the potential of the general processing system, might involve a process of differentiation where general cognitive resources become more specialized and fine-tuned for a particular domain. On the other hand, advances within an SSS, like moving from basic arithmetic to algebra, might rely more on coordination, integrating existing skills and knowledge into new, more sophisticated structures, like that symbolic encapsulation we just talked about.
Fascinating. So the mind develops on multiple fronts simultaneously, guided by these organizational principles, and progress in one area can have ripple effects across the entire cognitive system. It's a much more dynamic and intricate picture than just thinking about a single overall level of intelligence increasing over time.
Absolutely. It really highlights the interconnected and interactive nature of our cognitive development. It's not just one thing changing.
So wrapping this up, what are the key takeaways for us from this deep dive into Dimitri's model? What should we remember?
I think the central idea is that our minds develop along three interconnected paths: the efficiency of our general processing, the engine, our self-awareness and cognitive control, which is hypercognition, the driver or manager, and a set of specialized systems for understanding different aspects of reality, the toolkit. This development is guided by fundamental principles that shape how we interact with the world and how our cognitive abilities become structured. And maybe most importantly, progress in any one of these areas can have a positive impact on the others. It's all linked.
Right. And what might be some of the implications of this theory for, say, education or how we approach learning in general?
Well, the theory suggests that individuals will likely have unique cognitive profiles, right? With different strengths and weaknesses across these general processing abilities in the various specialized systems. So, educators could potentially use this framework to better understand how different students learn and maybe tailor their teaching methods to leverage both general cognitive strengths and domain specific aptitudes. It also highlights the importance of not just teaching content, the what, but also helping students develop their self awareness and cognitive control, their hypercognitive abilities, so they can become more effective and independent learners. Teaching them how to learn, essentially.
So it's about recognizing the multifaceted nature of intelligence and learning and maybe designing educational experiences that cater to these different aspects of cognitive development.
Precisely. Yeah.
This has been a truly eye-opening deep dive. It gives you a much richer appreciation for the complexity and, well, the elegance of how our minds develop. So for you, the listener, here's something to think about. How might understanding these different systems within your own mind, your processing speed, your self-awareness, and your specialized ways of thinking about different kinds of information help you tackle new learning challenges or better understand your own strengths and weaknesses in various areas?
Yeah.
Which of these specialized systems do you find yourself using most frequently in your daily life or your work? It's definitely food for thought.
Indeed. It encourages a more mindful awareness of our own cognitive landscape, I think, and how we engage with the world around us.